From Schrodinger's wave model, we have got quantum numbers. Three quantum numbers were discovered by Schrodinger wave model, from Schrodinger wave model, by one came from different sources, that also I'll tell you. See, for locating the position of an electron, four quantum numbers are prescribed. Some rules and regulations also are there. We will discuss those ones also. See, one of the quantum numbers, the first one and the first biggest one actually we should call that, is principal quantum number. The name itself tells this is the main quantum number. This is called principal quantum number. Second one is called azimuthal quantum number. Third one is called magnetic quantum number. And fourth one is called as spin quantum number. Out of these four quantum numbers, these three are discovered, are elaborated from Schrodinger wave model, while this one came from hyperfine splitting of hydrogen spectrum. We will discuss all the four. See, first one, principal quantum number. First understand, according to Schrodinger wave model, what happens, that first of all we will have a shell. Shell is the biggest part which we will have here. This shell, what Schrodinger says, will be divided into subshells. Then subshells again will be divided into orbitals, and in orbitals we will have electrons. Got it? So what happens here? Principal quantum number tells us about the shell number, in which particular shell the electron is present. The principal quantum number usually is denoted by the symbol n, and for a particular electron of a particular element, we can have any value of n starting from 1 up to infinity. Cannot be 0 obviously. Now, shells will be divided into subshells, and this is defined by azimuthal quantum number. So, you can understand one thing, that principal quantum number basically tells us about energy of the electron. How much energy will be possessed by that electron? That is what principal quantum number tells us. Second part is azimuthal quantum number. Shells are divided into subshells. Subshells are explained by azimuthal quantum number, usually denoted by the symbol L. Right. Now, for a particular value of n, we will have equal number of L values, starting from 0 to n minus 1. Means in first shell, we will have one subshell. In second shell, we will have two subshells. Similarly, in third shell, we will have three subshells. Now, these subshells are given by the number system 0 to n minus 1, as well as by symbols. We will go into details for this. See, what happens here, suppose we have got n equal to 3, one particular electron is present in the third shell. As per the quantum numbers, we will have 3 subshells into this. In a shell, we will have equal number of in a shell, we will have same number of subshells, whatever is the shell number. So, we will have 3 subshells here. Values will be given to them 0 to n minus 1. N minus 1 will be 3 minus 1 means 2. So, this will be 0, 1 and 2. These will be the values of L. So, we will have 3 values of L here, 0, 1 and 2. Means this will correspond to 3 subshells. These subshells also are given by symbols, alphabets S, P, D. Similarly, for subshell number 3, it is given as F. Right. Now, SPDF, usually they are called SPDF shells. These are the values given for them. For S subshell, the value of L is given 0. For P subshell, value of L given is 1. For D subshell, it is 2. Similarly, for F subshell as 3 and so on. Because obviously you can understand if there are infinite shells in an atom, there will be infinite subshells also, right? Now, come to third quantum number, that is magnetic quantum number, again important one. What magnetic quantum number tells us? Magnetic quantum number tells us about number of orbitals in a particular subshell. Understand? First we have shell divided into subshells, subshell again divided into orbitals. In the orbital we have got electrons, right? Now, so we are coming up to orbital now. Now, magnetic quantum number usually denoted by M, and for a particular value of L, there will be 12 plus 1 values of M, right? This is given in this way also, that we give the numbers also, and numbers are given as that we will have them from minus L to plus L including 0. Minus L to plus L including 0. It is not from minus L, 0 plus L, not this much only. Minus L to plus L including 0. We take up the example when L is given as equal to 1. Now you can understand we are talking about P subshell, because P subshell is given the value of L as 1. Now, if you see here, we will have 3 values of M, because L is 1. So this becomes 2 into 1 plus 1 here. So we will have total of 3 values. Which 3 values? Starting from minus L means minus 1. These are the values of M for a particular value of L. So starting from minus L to plus L plus 1 including 0. So 3 values of magnetic quantum number we will have here. These are the 3 values here. We will take up some complicated case. Here only 3 cases we have got here. See, if suppose value of L given to you is 2, means we are talking about D subshell. We are talking about D subshell. So when L is equal to 2, see how many values we will have. Minus L to plus L including 0. So we will have minus 2, we will have minus 1, we will have 0, we will have plus 1, and we will have plus 2. So 1, 2, 3, 4, 5, a total of 5 values we will have. And as we are discussed here, that M tells us about number of orbitals. Means in L equal to 1 means P subshell we will have 3 p orbitals. Similarly, L equal to 2 means D subshell we will have 5 d orbitals. Remember one thing, in a particular subshell all the orbitals will be degenerate. They are called degenerate orbitals. Remember, in a particular subshell all the orbitals will be degenerate. This is the term used here, one term we use. This is called degenerate orbitals. What's the meaning of degenerate orbitals? That all the orbitals will have exactly same energy. We are not talking about size and shape, but this is for sure that all of them in a particular subshell, all the orbitals will be at same energy level. There will not be a single point difference in the energy of those orbitals. So in P subshell, it is represented like this in form of boxes. This is P subshell. So all the p orbitals will be degenerate, exactly identical, p subshells especially, in all the aspects here. If you talk about d subshells, similarly in d subshell we will have 5 d orbitals. This is p orbital. In d subshell we will have 5 d orbitals. This is called box system to show them. 1, 2, 3, 4, 5, like this. And again all these 5 orbitals under normal conditions will be degenerate. Remember, d orbital split in case of coordinate compounds, but not under normal conditions. If you change magnetic field, electric field, that time the energy level change, but under normal conditions they will be exactly at same energy level. There will be no difference at all. Now come for the fourth quantum number, that is spin quantum number. Spin quantum number, this talks about the electron present in a particular orbit. See, in one orbital we can have a maximum of 2 electrons which spin in the reverse direction, in opposite directions. If one of the electron goes clockwise, other electron will go anti-clockwise. Now, for spin quantum number, for these 2 electrons, values are given as plus half and minus half. For spin quantum number, it is denoted by small s, like this. Only 2 values will be there, because in one orbital we can have only a maximum of 2 electrons. So, for one of them, it is plus half. For other one, it is given as minus half. Remember, there is no correlation between upward and downward spin with plus half, minus half, or clockwise or anti-clockwise. But one thing is for sure, that in an orbital, if one electron is clockwise, other one will be anti-clockwise for sure. And for one electron, if you give the value plus half, the other one must be given minus half. Similarly, we show them with sign also. One of them is shown with upward arrow, other one is shown by downward arrow. Again, if this is clockwise, then this will be anti-clockwise, and this is anti-clockwise, then this will be clockwise. Right? So, this is spin quantum number. We will discuss here shapes of orbitals. Here, basically in the syllabus, we will have SPD orbitals. So, we will discuss more about them. S orbital, in whatever shell it may be present, S orbital is one orbital which will be present in all the shells. Now, it is spherical, and electrons are distributed in this symmetrically in all directions, in all dimensions. So, this is a perfectly symmetrical orbital, right? Spherical, not circular, spherical, right? P orbitals, on the other hand, are said to be dumbbell shaped, like this. We say this is P orbital. Now, as you know, just we have shown here that there will be 3 P orbitals, and they are named as Px. If this is x-axis, then this becomes Px, Py, which will have along y-axis, and Pz. We will have 3 P orbitals, Px, Py, and Pz, like this. 3 P orbitals we will have here. Okay. Now, next d orbitals. This is S, this is P. D orbitals, 5 d orbitals we have, and here comes a bit complication. How? See that part. We have 5 d orbitals, dxy, dyz, dxz, right? These are 3 orbitals. I will tell you how they are oriented. dx square, y square, and dz square. 5 d orbitals we have got. How they are oriented along the axis? See that part. If we assume this to be x-axis and this one to be y-axis, z will go like this. The dxy will be oriented in between x and y or axis. Means it is a double dumbbell shaped orbital, and it goes like this. This is dxy orbital here. This will be known as dxy orbital. Similarly, we will have dyz orbital, and dyz we will show like this. If we assume this is y-axis and this is z-axis, then we will have yz orbital oriented in between y and z-axis in this manner. This will be called dyz orbital. exactly in similar manner, we have got dxz. Obviously, dxz will be oriented in between x and z. So these three orbitals, dxy, dyz, and dxz, these three orbitals are oriented in between the axis. Right? Come for the fourth one, which is dx square y square orbital. See this one. Dx square y square is the orbital which is oriented along the axis. Means if this is x axis and this is y axis, then dx square y square will be oriented along the axis like this. This orbital is known as dx square y square orbital. Come for the fifth orbital, which is dz square. This already we discussed, dz square. This is a bit complicated one, and what happens in this case, that here two lobes of the orbital are oriented along the axis, along z axis like this. This is z axis here, while it is believed that remaining two lobes fuse with each other to form a disk around the orbital. It is shown like this. Remember, this is a disk, not a circle. In this manner, a disk is supposed to be maintained, supposed to be made by the electrons. Remember, orbital is that space around the nucleus where probability of finding the electron is maximum. So remember this, we calculate from Schrodinger wave equation. When we calculate what the probability of finding electron at this distance from the nucleus, it is the picture which comes out. We will have probability of finding electron here. This also is dotted area actually here, as well as around disk. They go, two lobes go like this, and we will have a disk here like this. This is the disk here, right? So this is how we get dz square orbital. This is called dz square orbital, right? So in this manner, we have got total of 5 d orbitals. Again, in case of d orbitals, no doubt the shape of this fifth one is different, but energy wise, all the 5 orbitals have got exactly same energy. There is no difference.